All right, everybody. Welcome to the last video for floor 7, where we're dealing with queues. In our first video, we got our queue working. Our self-test check on the queue returned all phases green. In the second video, we did hot potato. We implemented the hot potato function where it played the game. It returns the real survivors from hot potato, which is where you have a group of entities, and every kth person in hot potato gets removed. So we did different tests on that and did some edge case testing as well. And today we're going to actually finish the floor with the simulate dispatcher. So we're going to drain an enemy line in arrival order. And then we're going to do this little board exercise that builds a working queue out of 2 stacks. Okay. So the key hazard to look out for is whenever we bind a reference to the front action before we dequeue. Dequeue destroys the front node. If we dequeue first and read after, we read the wrong action or freed memory. This is the same bug shape as last week's undo, is the bind before you pop type of philosophy there. And in the last video for floor 6, I told you this would come back, and here it is. Okay, so let's go ahead and let's build our executable here and kind of show where our simulate is at right now. Let's go ahead here. Once we load in, you'll notice we have a provoke name where we can enqueue an enemy action into the line, and then we have a simulate where we can drain the enemy line. So I can say I want to provoke the goblin, let's say. So goblin takes a number and joins the line. I can then try to simulate, but then you see, of course, it's not yet implemented. Okay. So we have 2 commands. Provoke the goblin worked, and it has quietly since we started this floor. Provoke has been, what it does is just enqueues each enemy's action onto the line, ready to resolve. But simulate itself is still a stub. The line is filling up, but nothing can drain it. So today we're going to write the drain, which is going to be a short loop, and then we're going to take the queue apart and then build it out of 2 stacks, as I mentioned before, just to prove the ADT and the storage are different things. So let's go ahead and let's open main.cpp, and we will find us the simulate command here. So we'll collapse this folder here. We'll say main.cpp here. Okay. Now let's go on down here. We'll do Control F to find simulate here. Okay, perfect. So there's that right there. Now, here's essentially an English description, real quick, of how simulate works. Okay. So provoke enqueues an action at the back of the line. Simulate resolves them from the front. Okay, so turn 1 is whoever arrived first, turn 2 the next, and so on until the line is empty. Okay. All right, back here. Sorry, I had to leave there for a second. My dog came in with a treat, and he was macking on that thing. He was making some noise. Okay, so turn 1 is whoever arrived first, turn 2 the next, and so on until the line is empty. That's the whole point of floor 7. The queue is what makes the resolution fair. A goblin showed up first. The goblin acts first. There's no cutting. The body here is going to be a short loop, but there's one ordering trap, and it's an old friend of ours. In the last floor, with undo, I told you bind the reference to the top action before you pop, okay? Because the pop destroys it. Same thing here. We read the front action, we use it, and only then do we dequeue. If we dequeue first and read the front after, the action you wanted would actually be gone. You'd either print turn 2's action on turn 1 or read a node the queue just deleted, okay? So let's go ahead and get into our stub placeholder here. be this guy right here, and then I'm just going to delete these comments here. Okay. So if we're on simulate, I'm going to say if our hero dot enemy action queue is empty. Okay, so if it's empty, I'm going to say standard cout. We'll say no enemies are in line. Use provoke name first. So we'll just say something like that. Else, we can say standard size t of turn is equal to 1. I can say while not our hero dot enemy action queue is empty. Press a little while loop. I'll say const standard string ampersand action is equal to hero dot enemy action queue dot front. So we'll read the front. I'll say standard cout. I'll say turn. We'll do our turn, and then I'll say colon space. Then we'll say action. Oh, that was weird. Anyways, there we go. Backslash n right there. Okay. We'll say hero dot event log dot push front. And to the front, we're going to say, I'll blow this out so we can kind of see it a little better. I'm going to say simulate turn plus standard to string turn plus, we'll put string literal with a colon and a space plus our action. Then we'll close the parenthesis there and do our semicolon. And then we'll say hero dot enemy action queue dot dequeue. Dequeue. Okay, that's how you spell D. Yeah, okay. And then we'll say plus plus turn as such. Okay, so I'm essentially saying we have our turn starting at 1. We're going to say while our enemy action queue is not empty, we're going to get our action by reading the front. We're going to print it out, what turn we're on and the action, and then we're going to push that onto our event log. We'll then dequeue, and then we'll increment our turn there. Outside this while loop, I'll say standard cout. All enemies have acted. The line is empty. Okay. Perfect. And that should complete us here. So first, the guard, if the queue is empty, say no enemies are in the line and stop. This is not going to be optional for us. Front on an empty queue dereferences null, the underflow we guarded against in hot potato. We check empty before we ever touch front. The ADT does not protect you here. Your caller must. Then for our else branch, in the trap here, a turn counter starting at 1. Okay, now we loop while the queue is not empty. Inside, we build a const reference to the front action. That's the const standard string ampersand action. And we do it before we dequeue. Now, we print our turn, right? Turn in, and the action, we push the event log entry. Then we dequeue. That's the last thing in the loop body. After we're done reading, then we bump the turn. If you dequeued first, action would point at a node pop front, just destroyed. We bind, use, then remove. Order is the whole bug, and it's the identical shape to last week's undo. The rule travels with you in this case. So we read before we remove. So let's see now if we build our executable here. This command here should make it to where we're ready to rumble. So I should be able to provoke a goblin, provoke a skeleton, provoke an imp. Got 3 enemies here. Perfect. So I could simulate. Turn 1, goblin stirs in the dark. Turn 2, skeleton. Turn 3, imp. Boom. All enemies have acted. Perfect. So you see, once again, 3 provokes, 3 enemies in the line. Goblin, skeleton, then imp. Simulate resolves them in exactly that order. Turn 1, goblin. Turn 2, skeleton. Turn 3, imp. FIFO, first in, first out served. If this were a stack, imp would have gone first, right? The most recent arrival. And the fight would be unfair to whoever showed up early to get beaten by the dungeon crawlers, right? So the queue is the fairness here. Now, of course, if I run simulate again, right, no enemies are in line, okay? The line is empty now, and the guard actually fires for us, okay? And that's better than a crash when we try to use the front method there. So that empty check is the contract talking there. Now, this is going to settle our code, but now I want to talk to you about building a queue out of 2 stacks. So we're going to move on over to a notepad session here. Okay, so here we are in our notepad here, and the question is, can you build a FIFO queue out of 2 LIFO stacks? The answer is a big resounding yes. It is a classic interview question. So here's the shape. So we would have us a struct, we'll call it a stack queue of type T. Okay. Within that, we could say we have a stack of T. We'll call it in and out. So we have a couple of those. We'll have a void in queue type T called V. We'll say in dot push V. We have a T ampersand front. Sure, I'll kind of tab this over to kind of line everything up here a little easier for us. And then right here, we'd have transfer, return out, top. Okay, we have a void dequeue. And for dequeue, of course, it'd be transfer. Let me say out, pop. Okay. And then we'd have in the private method section, we'd have void transfer. We'd say if out empty. I don't have to do a bracket right there. You can just do it like that. I could say while not in empty. I could say out push in top. See, that needs, yeah, there's 2 closing, and I can say in pop as such. Boom. Put that one right there. That would go right there. And that would go right there. Okay. So I should have us all good to go. Okay. This should be good. So we have 2 stacks here. In queue just pushes onto in. The magic is in the transfer. When we need the front and out is empty, we pour in into out. So we pop each off in, we push onto out. Pouring one stack into another reverses it. So think about it like this, right? So we have our stack, we have the in queue, we can push. With the front, we can, of course, if we need to, right, while the in is not, empty, we can push with our output, our in top, right, and then pop it off. So you see, we're just transferring here. So let's think about this. If we said, okay, if I enqueue 1, 2, 3, then in has 1, 2, 3 with 3 on top. Okay. And then if we call front in that case, then what's going to happen? So we call front, our out is empty, so we transfer, right? So when we transfer, we pop 3, we push 3, we pop 2, we push 2, we pop 1, we push 1, right? Now our out has 3, 2, 1 with 1 on top, okay? So now we say out.top is actually 1, which is the first thing we enqueued, right? Oh, so that is FIFO. And that is built from 2 LIFO piles. Isn't that cool? And so here's the main thing and the deep point really for all this and the whole floor here. And here, I'll kind of compress some of this up so we can kind of see it all together here. So here's the main thing. This stack queue has the same 5 method surface as our queue. Same enqueue, same dequeue, front, size, empty. So it satisfies the same ADT contract, okay? You could drop it into self-test queue and it would pass, but inside the storage is completely different. Not one chain, but 2 stacks and a clever transfer. The ADT is the promise, the data structure is how you keep it, and they're not the same thing. That's the sentence floors 6 and 7 exist to teach us. So, hopefully this was helpful for you. And I tell you what, real quick, I'll throw this into a quick example, and we'll kind of showcase that this works as expected. Okay, so I kind of cleaned this up and threw it in a little online C++ compiler just to show you real quickly. So we build ourselves a little template here, and we have ourselves our class queue from stack, where we have 2 stacks, our in and our out. We transfer when the output stack is empty, so kind of what we saw before here with our void transfer. So if the output's empty while the input's not empty, we push. So we move what's in the top over to the out. We pop what's on in. We then have our public method. We have enqueue, of course, where we can push our value. We have our front, where if we're empty, of course, we'll throw an error. So I had some error handling here. If not, though, we'll transfer, and then we'll return the top, right, because we're doing the front. We also have our const version here as well, which in this case, I just kind of filled it in just with a logic error because, I'm just trying to do a real quick example here for you. We have dequeue, of course. If it's empty, we'll throw out a problem and say, hey, can't dequeue from an empty queue. Otherwise, we'll transfer and we'll pop what is on the out. And then I have an empty method, right, where if both in and out are empty. And then we have the size, just taking the size of both the in and the out. And then in my main, I am creating me a queue that holds integers called nums. I enqueue 1, 2, 3. And then I go ahead and I say, while nums is not empty, I'm going to output what's at the front. And I go through and dequeue. And when I run this, you see I get 1, 2, 3. So the original first in, first out type of structure there is kept, no problem at all. So I hope this was helpful just to see another example, building a queue from 2 stacks. Now let's just step back. So we did 4 one-line methods, and with them we got our hot potato game. We got a fair resolution loop. We got a queue rebuilt out of 2 stacks. Same 5 method adapter we wrote in the last floor, opposite in pairing, that is the payoff of an ADT. The promise was tiny. What it unlocks, though, is enormous, and you've now seen it twice. Now, 2 warnings on the way out. Grix will tell you to skip the empty check before front. Just read it. It's usually fine. On an empty queue, that's a dereference on a null, a crash far from the mistake. The guard isn't being paranoid, it's the contract, and the floor's own monster, the eternal backlog. It's the opposite of last floor's hollow echo. The echo struck when you read an empty stack, which was underflow. The backlog strikes when you enqueue and never drain. So you provoke 10 times, simulate 0, and the line grows without bound until you're out of memory. A queue that only grows is a queue that's wrong. If something produces, something else must consume. So hopefully that's okay. And I hope this was helpful. And I will see you in the next floor. Bye-bye now.